Welcome to the third installment of 6034 Fall 2020 recitations. Today recitation 3, we're going to be talking about constraint satisfaction problems, abbreviated CSP. Occasionally I'll refer to them as constraints problems, but this is the third installment of, in this case, the semester, representing problems in ways that reveal redundantly said the constraints that allow us to solve them. So it's the third time that we'll be using the tools we learned in the first recitation in search to solve problems in novel ways. So briefly showing you the agenda, we're going to be talking about DFS in the context of constraints, DFS as in depth first search, plus forward checking and propagating singleton domains. I'll explain shortly what that is. Depth first search, forward checking, propagating any domains, and then domain reduction before performing search. And this will be one of the more practical recitations, and that's because I'll be relying more on example problems to deliver the concept rather than being a little bit more theoretical as in the previous two recitations. Before we start, I want to present the first motivating problem that we'll be using throughout this recitation, and that's the time traveler's problem. The premise is that for MIT's opening of the College of Computing, you travel back in time in search for some of your favorite scientists and philosophers and engineers of all time. And you're going to bring them back. The issue is everyone wants to see at least a few of them, and according to the departments people are in, physics, history, philosophy, computer science, mathematics, there are constraints in between when you can assign each speaker, because you want as many people as possible to be happy, and as in minimum conflicts between the people that you want to watch. And I'll name a few of the invited speakers just so that you have an idea of what we're dealing with. The first invited speaker is Turing. So you know everyone from computer science is going to watch that talk, and also Lady Lovelace. We have Niels Bohr, Marie Curie, Shirley Ann Jackson, Plato, and Newton. And you're trying to find a spot for, or you're trying to find an assignment for each of these speakers that makes sense. And by that, I mean that there's the least amount of conflict in between all of them. So the most amount of people possible are happy with the assignment because they can attend the talks that really interest them the most. And before getting started, let's talk about a little bit of vocabulary. First, these nodes in the graph are variables. These are the nodes that we would use in a search problem. And each variable has an associated domain. And so the domain is the set of values to which you can assign a particular variable. And in the first, obviously we'll see what this means in the first example. So I'll just relegate the explanation over to the first example of depth first search. And now lastly, the edges connecting two nodes are the constraints. And what that means is if two nodes are connected to each other via an edge, those two nodes cannot take on the same value. Within 6034 context, of course. So now with the context, let's start talking about how we're going to use the tools that we saw in recitation 1 and recitation 2 in search and games in solving constraint satisfaction problems. So we have depth first search, and how it works is you make an assignment I'll show you briefly what that means. But roughly explained, it's that you take a value from the domain of a variable and assign it to that variable. And then after you make that assignment, you check for contradictions with past assignments. And what if you find a contradiction? Or what if you run into a dead end? That you find that the assignments that you have don't have a solution at the very end. So that's when you backtrack. And remember that in DFS, you're always exploring deeper first and nodes on the same level later. So let's say you find that this is not the path. Then you would switch to this one, but let's say none of these are the path. Then you backtrack all the way back to another node and you continue exploring. It's DFS. It's just that I make the drawing because in constraint satisfaction problems, sometimes it's harder to see how the methodology that we're following relates to DFS. So let me just make a little cloud note here. Backtracking is either uncrossing. You'll see what that means. I keep promising a lot for this upcoming example, but I promise I will deliver. Uncrossing or unassigning. Let's keep that there. Okay. So on with the first example. In these types of problems, in 6034 at the very least, we'll give you the order in which we want you to perform the search. And that's precisely what's here. I'll be making the variable assignments in that order. And so I had it half circled already. When I am going to make an assignment, I'll try to remind myself to circle it on the graph per se, as is here. So I would do the following, and I'll write the node that I am, and circle the node, write it and circle it, the one to which I'm assigning. And I'm going to start returning, that was the first one given to us, and there's only one possible value to assign to it. So that's, I'm assigning it to a value of 1, and now I need to assign a value to Lovelace. Lovelace's domain is 1 through 4. This is depth first search, which means the leftmost child is the one that is assigned. And the second step is to check for contradictions. I see I have an edge here, which means Turing and Lovelace cannot have the same assignment, and I've already given it a 1, so this needs to go. And I assign a 2. I check again for contradictions, and it seems to work. I'm only concerned with this edge. Let me finish highlighting this. There we go. And now on to Niels Bohr. I have a full domain again. And again, this is depth first search, so leftmost first. And it doesn't seem to conflict with anything, which means I can just proceed. Lucky for us. Now, Marie Curie. I'll make the assignment. And now I need to check. There's a conflict here, so it's definitely not 1. Next assignment. and there's a conflict here. Whoops. It's not a 2. Then the remaining value, well, there are 2 remaining values, but now I assign it to 3, and there doesn't seem to be any problem with 3. So now Shirley Ann Jackson. Again, depth first search. So 1 is the assignment. There seems to be no problem there. Now, Plato. I assign it a 1. And again, I run into a conflict. Let's assign it a 2. And am I conflicting with anything? Yes. Here I have that edge that doesn't allow me, or that constraint, better said. So it's, whoops, not a 2. Let's try 3. And I quickly run into a conflict with Mary Curie. So 4 is all that's left. And luckily, I don't have any conflicts there, so I can continue to Niels Bohr. Not Niels Bohr, Newton. Apologies. Let's see. First one, there's a conflict with Turing. That's a no-go. What about 2? That's a conflict with Lovelace. Three, I assign it, and I see that it is a conflict with Mary Curie. So 4 is all we have left. But we have a conflict with Plato here. This is very sad. So what happens now is we have to backtrack. And you would think, oh, I'll just backtrack back to Plato, but there's no, in the case of Plato, we assigned it to the last possible value that we could. All other values had a conflict, which means we don't really backtrack there. We backtrack here, because this is the last place where we could change the assignment, conceivably. I encourage you to finish this exercise on your own. This is the, let me write that this is a backtracking. And technically, every time I crossed out an assignment and moved on to the next one, that was also backtracking. But this is a larger backtrack. Okay, I encourage you to finish this exercise on your own. It'll make you very handy, and it'll get you comfortable with DFS. Now I want to go back, because now I want to talk about DFS plus forward checking. And I want to be cautious about it, because I've noticed in my years of taking the course in TAing that this is the difference between DFS and DFS with forward checking gets very hazy, and a very commonly made mistake is that we inadvertently do DFS plus forward checking just because it's so natural, thinking that it's DFS, when in reality it's not. And DFS with forward checking, I hope to the relief of many of you, is basically avoiding this back and forth of assignment, I unassign and I go back and assign something else. Because I write number 3 3 here because the first 2 steps apply. I first make an assignment, I check for contradictions with past assignments, and then after the assignment, eliminate contradictions from the neighbors. And I want to highlight from the neighbors. Okay? And now, let's see how that looks. Things start off the same. I still start with Turing, and it's still a 1. But now is where, let's say I checked for conflicts, and no other variables have any assignments, so there are no conflicts. But now I check for possible constraints, or how do we call them? Contradictions in the neighbors. So now I'm going to look ahead, I'm going to forward check, and I'm going to see that Lovelace has a 1, but because Turing is assigned to a 1, I have to cross that out. And Newton already also has a 1 in the domain, but that has to go. So I'm just going to cross out those 1s before they become a problem later. And now I go ahead and make the assignments. And off the bat, notice immediately, in the case of Lovelace, I'm already skipping an assignment that I would have made just to backtrack. Okay. Give me 2 seconds. Okay. I assign the 2 to Lovelace. And now I check for any contradictions. There don't seem to be any. And now I forward check onto the neighbors. Plato is connected to Lovelace. It can't be a 2. Marie Curie also can't be a 2. Newton can't be a 2, and I believe that is everything that is connected directly to Lady Lovelace. Whoops, that procedural note. I should have circled. I circled the number 2 under Lady Lovelace on the graph, but I forgot to circle it on the tree to the right-hand side. Make sure to be procedural about it. Do as I say, not as I do. Okay. After Lovelace, we're going on to Niels Bohr. And so far we haven't eliminated any constraints from Niels Bohr. So we have eliminated any values from the domain, not any constraints. Okay. This is DFS. So I assign it to a 1, and I have to forward check. It's only connected to Newton, whose 1 from the domain was already eliminated, but Marie Curie still had a 1. Now she no longer has a 1 in the domain. And it's her turn for the assignment. She gets either 3 or 4 DFS, so I pick the first one. Now forward checking. Plato loses a 3, and Niels Bohr loses not Niels Bohr, dang it. Newton loses the 3. And you'll notice I don't eliminate it from Lady Lovelace because that is a variable whose value was already assigned. And because a value was assigned to that variable, there's no need to work with the domain anymore. It would actually be incorrect to eliminate it from the domain at this point. So I strongly discourage you from marking anything here, or as in crossing values off a domain after an assignment has been made. You can do that much after if you backtrack and unassign Lady Lovelace. Then you can cross out other values from the domain. Okay. We have Mary Curie assigned. Next is Socrates. No. I'm starting to mix up all the historical figures. Shirley Ann Jackson. We haven't eliminated any values there. And we DFS. We check for any violations. There are none. And let's forward check the neighbors. Only Plato is a neighbor. So we eliminated 1. Thankfully, we just have the 4 left. We make that assignment. We forward check. And now, sad face. Because Newton doesn't have any values remaining in the domain. And we need to backtrack. But notice already that even though we had to backtrack anyway, the number of steps that we had to go through in order to get to the point where we backtracked was far fewer than in this case. So forward checking, even though it doesn't guarantee us an optimal solution off the bat, already improves a lot of the redundancy and wasted work of just straight depth first search on this constraints problem. So that's DFS plus forward checking plus FC, just because it's a bit of a mouthful to say it every single time. And now I want to introduce another further optimization that you can do on it. DFS plus forward checking plus Prop-1. And what does that mean? It means that you propagate singleton domains. And I'll explain what that means. Because this is in addition to DFS plus forward checking, it actually happens after step 3. After you perform the forward checking, check for newly created singleton domains, and then number 5, if yes, cross out conflicting values from their neighbors' domains. Okay. Now let's work through an example. I can't remember whether I defined a singleton domain, but just in case I didn't at the beginning of recitation, let me briefly say a singleton domain, or a singleton domain is a domain where there's only one value. And I would refer to Turing as a singleton, or as a variable with a singleton domain. I'm not going to start by propagating that singleton domain because I'm going to follow the rules to the letter. And what happens is I start by making an assignment because it's DFS, and I check for conflicts, I forward check, and then if I create a singleton domain, I'm going to propagate it forward to the others, through the neighbors' domains. And here I don't have a case of I haven't created the singleton domain, it already exists, and it just so happens that it's the first variable that we assign. So I still have to go through step 1. Let's do just that. Step 1, assign, and it's still forward checking. So much as we did before. This is going to look familiar. Lady Lovelace, assign it 2. This can no longer be a 2. This can no longer be a 2. And for Newton as well. Niels Bohr still has his entire domain. This is A1, which means Marie Curie loses 1 from the domain because of forward checking. And now on to Marie Curie. So far, it's exactly the same as DFS plus forward checking, because that's all that we've done so far. This is A3. Let's see. Which means this Plato loses 3 and Newton loses 3. And this is where things start getting interesting. With this assignment, Newton is a singleton. After the forward checking step, I've created a singleton. So what happens? I'm going to go to Newton. I'm going to see, okay, Newton has a 4 left in the domain, which means it basically must be assigned to a 4. Otherwise, the whole problem is not going to work. And I check its neighbors. Marie Curie is already assigned a variable, or a value. Lovelace has already been assigned a value. Just Plato is missing. And so I'm going to cross out this 4 because Newton needs it more. But hey, now by doing that, P is a singleton. And I repeat the same steps. There's a 1, therefore Plato must be a 1. And I go to to Shirley Ann Jackson, and she has a lot of options. She won't mind losing 1. And I check again to make sure that I haven't created any new singletons, and I haven't, so I can proceed with the assignments. With the newly reduced domain, Shirley Ann Jackson has 2, 3, and 4. I assign her to a 2. Plato can be a 1. And then Newton can be a 4. And we are done. So you see, Prop 1 already allowed us to get to a good solution just off the bat. We didn't need any backtracking by propagating the singleton domains. And it's not guaranteed to work every single time, but it's a good step forward. There are cases where Prop 1 wouldn't work, but there are ways to optimize this even further. And instead of propagating singleton domains, what if, for example, every time I did forward checking and I eliminated a value from the domain of a neighbor, I propagated those further. And that's what this next method is going to be. It's called DFS plus forward checking plus Prop-Any. again, this comes after forward checking. After DFS plus forward checking, propagate, any reduced domain, which means anytime a variable loses a value from its domain, you have to propagate that value to, or that variable to. And I'm going to show you how to propagate in the next slide. We haven't seen any pseudocode yet, so I think it's about time to integrate it into this recitation. Okay, so let's say, reminder, this is DFS, and in the big search recitation, we always had the notion of a queue. So now we have, because we're dealing with constraints and propagating variables, we're going to have a prop queue. And let's say my prop queue has a variable v in it. And that means I have to propagate the values in, or the values in the variables, the values in the domain of v. This terminology is a bit clunky. Okay. So first, let's assume you're in a loop and you pop v from the prop queue, which means you're working with v directly. So the first step you would take with v. Look at v's domain. In other words, it's options. Then, for each neighbor n in basically v's neighbors, so for each neighbor, I'm going to check each value in that neighbor's domain. I'm going to use a lowercase b. I'm just going to use the value for each value. In n dot get domain. So this just gives me the values, a list of the values in the domain of the neighbor that I'm working with at the moment. If, and here comes an important detail, let's say I have this function incompatible. And it's going to tell me whether a particular value in the domain of the neighbor and all the values in the domain of v are incompatible. So what that means isn't, let's say I'm working with value, let's say n has a domain of 1 and 2. And let's say v has a domain of 2, 3, 4. And let's say for some reason that let me think about it. 2 and 3, sorry. I'm going to change this example to 2 and 3. Let's say that for some reason n and v cannot take values that are 1 apart from each other. So if I assign a value of 2 to n, I cannot assign a value of neither 2 nor 3 to v. So if I were to assign a value of 3 to n, I wouldn't be assigned a value of 2 nor 3 nor 4. But if I assign a 2 to n, I can assign a value of 4 to v, just because of this magical constraint that I made up. In this example, 3 conflicts with every single value in the domain of v, which means this is the value that I want to eliminate. But if I were to select 2, v can still be 4. So there's no problem there, and I can leave 2. So what this function incompatible does is it tells me whether that value is incompatible with every single value in the domain of the variable of interest. Again, we'll do an example to make this clearer. So if it is incompatible, I'm going to remove that value from the domain of n. And because I've removed the value from the domain of n, and this is Prop-Any, I need to add n to the prop queue. Now let's work through an example. Pardon me just a second. Okay. In this example, this is changing to the other quiz that I mentioned, 2011 Q2, quiz 2. You're setting up a petting zoo, and for some reason you have an evil lion because you have a strong preference for evil lions instead of llamas, and a hornbill and an antelope, and you're trying to assign them to pens. This is the shape of the corral, or the pens that you're trying to arrange. And you have the following set of constraints. The evil lion cannot be assigned to the same pen as the hornbill, because the evil lion would just kill it. It cannot be assigned to the same pen as the antelope, but there's the additional constraint, and this is similar to the example that I gave earlier. They cannot be adjacent. And what does this mean? It means that if the evil lion is here, the antelope cannot be here. It must be here. And I've already given you the order in which you must do the assignments. It's first going to be the hornbill, then the antelope, then the evil lion. Okay. So I'm starting. My prop queue is empty because I haven't reduced any domains. So I just start with the standard DFS. The first assignment is the hornbill. And the hornbill gets a value of 2. Now I do some forward checking. I'm going to avoid writing on the drawing, because if I do any backtracking, it's going to be hard to erase around and it's going to become very scribbled. So I'm going to keep the drawing as clean as possible, and I'm going to write all the relevant information on the table. So I have assigned it a value of 2. I check with the evil lion. It cannot be a value of 2 anymore. And there's no backtracking yet. But I've reduced the domain of the evil lion, which means I need to add it to the queue. Okay, and actually a misnomer. I named this column value assigned, but in reality it should be value assigned or propagated. And the reason is, I've made an assignment. I did the forward checking, I eliminated a value from the domain of one of the neighbors, and I've added it to the prop queue. Now I can't make any further assignments until the prop queue is completely empty. So the evil lion goes here, and that's why I made the correction from variable assigned to propagated, or to assigned or propagated, because the evil lions, I propagated a value through the evil lion's domain, and I'm propagating it forward because of the prop queue. So I've added it there. That means I've removed it from the queue. And I think, okay, so the evil lion can't be a 3. I mean, can't be a 2. So it can only be either a 3 or a 4. Now, I go, think back to the incompatible function. The hornbill is already assigned. I don't care what the domain of the hornbill is, but the antelope is still unassigned. If the evil lion takes a value of 3, 3 is out of the question for the antelope, and because of this particular constraint, it can't be a 4 either, because that would make them adjacent. And now let's say it's the same thing for the 4. It can't be a value of 4, and 3 is adjacent, so it can't be that either. So the following happens. Now suddenly, my antelope has an empty domain. So what's the solution? We backtrack. I didn't add it to the prop queue because, just a note, because I ended up with an empty domain and I'm backtracking. So it's like in this case, because I'm backtracking from the second step to the first step, it's like hitting the reset button. Because I've backtracked, assigning the hornbill to a 2 doesn't work. We'll assign it a 3. And we propagate the evil lion. Cannot be 3. There's no backtracking. But we add the evil lion to the prop queue. I pop it off, and I propagate that constraint further. Now, let's think again. The evil lion can't be 3. It can be 4. If it's 4, the antelope can't be 4 nor 3. But if the evil lion is 2, it cannot be 3 again, but it can be 4. So there's a case where 4 is a valid assignment for the antelope, but there's never a case where 3 is a valid assignment. So 3 is the value that we're going to eliminate. And there are no empty domains yet, but we've just eliminated a value from the antelope. It's 3, and it's not an empty domain, so we're not backtracking, which means I add the antelope to the prop queue. I pop it off the prop queue because it was next in line. And now I think the antelope can only be 4, which means the evil lion definitely cannot be 4, and 3 is no longer in the domain because we eliminated it earlier. So 4 is incompatible with the entirety of the remaining domain of antelope. So we remove this. No backtracking yet. I've propagated the evil line. Let's see. Evil line. There's nothing to change because there's only one value in the evil line's domain. And it's not conflicting with anything. Now I assign antelope is equal to 4. No conflicts anywhere. And the evil line is equal to 2. No conflicts anywhere. And we're done. So you see now that Prop-Any sped up. We had a moment where we did have to backtrack, but the number of steps required was far fewer. As we were going, we were eliminating constraints here and there, and ultimately we ended up performing fewer computations than had we waited for singleton domains. Now there's one further technique. This is the last one that I'll show for today, and that is domain reduction. And this is the same process as Prop-Any, so the same steps, the same pseudocode, except, and I'll start writing it down. I got ahead of myself. Same process as Prop-Any, except all variables. I was starting to get the hang of it too. Whoops. All variables start on the prop queue before the search begins. So let's redo the example with the petting zoo. So reminder here that I only started adding variables to the prop queue after I had gone through all the steps of DFS plus forward checking, and I modified, in this case I modified the evil lines domain. What the premise of domain reduction is, I'm going to put all of them on the prop queue before starting anything. So the hornbill equal to 2 is not going to be the first step. See, I've added them already. And I've added them in lexicographical order. So if, at least within 6034, if we don't give you the order in which to start if we tell you, here's a domain reduction problem, and we don't tell you in which order to add the variables to the prop queue, just put them in lexicographical order. It's a good rule of thumb to do things in 6034. Okay. So let's start with the antelope. I look at the evil lion, which is where the constraints happen, and if the antelope is a 3, the evil lion can either be 2 nor 3 nor 4. If it is a 4, it cannot be 3 nor 4 either. So in both cases, the evil lines 3 and 4 are in conflict with any variable assignment from the domain of the antelope. So the evil line cannot be 3, and the evil line cannot be 4. And there's no backtracking. Oops, I forgot to cross this out. And I've remember this is Prop-Any. I've just reduced the domain of the evil line, so I'm going to add it back to the prop queue. Here it is. Now I pop the evil line off the prop queue, And remember, now it's a singleton. It only has 2 as a possible value in the domain. And I'm going to look here. If evil line is a 2, it can only be a 2. The antelope can never be 3 because they cannot be adjacent. So the antelope cannot be 3. And now let's look at the hornbill. If the evil lion is 2, it definitely can't be a 2, and the hornbill can be adjacent to the evil lion, so 2 is the only problem. And again, as I said earlier, a good rule of thumb is to just add things lexicographically. So I'll add the antelope first and then the hornbill. Okay? Now I pop the hornbill. It's either 3 or 4. Either 3 or 4 because the evil lion removed the 2, and 3 and 4 are not in the domain of the evil lion, and this is the only constraint the hornbill has, which means we don't really do anything. No backtracking either. Let's put the evil lion back. Now, the evil lion is a singleton and nothing has changed, so we keep it the same. Now the antelope, nothing has changed, and let's just finish up with the hornbill. And nothing has changed. And so now we can start making assignments. It just so happens that this problem has made everything basically a singleton, except the hornbill, but we're starting with the hornbill. So the assignments would look more or less like this. I would assign a hornbill to the first possible value, that's a 3. Then I'm running out of space, so I'm going to do it sideways. Then what was the assignment order? I think it was the evil lion afterward. Whoops. Yeah, hornbill, antelope, evil lion. The antelope can only be 4, and the evil lion can only be 2. And you're done. So I wouldn't say this was an optimization to the algorithm on top of Prop-Any, but it was something we basically inspected the tree or the domains of the variables, and we determined, okay, these domain values are inconsistent in a way, and we've effectively reduced the number of computations that we needed before even starting the search. So that was yet another optimization on top of it. And you can see by the number of steps that, although roughly similar, we didn't even backtrack this time, and we got to the final assignment. You know, once we started assigning variables, there was no propagation happening of constraints. Okay, so one thing that I would like to encourage you to do is to perform either Prop-Any or domain reduction, or both, ideally both, on the panelist problem, the time travelers problem that we were discussing at the beginning of Recitation. And it's a long problem, but I truly believe that if you complete that problem successfully with all the correct steps and methodically, you will have a very solid grasp of the concepts of, at least for a Prop-1, perhaps propagating singleton domains, propagating Prop-Any, and domain reduction. So I've included this table in the boards that you can work on, and of course once you're done with the domain reduction, then you can go ahead and make the assignments and see how much those speed up. Okay, So today we've covered constraint satisfaction problems, among them plain DFS, depth first search with forward checking, and adding two different optimizations, propagating singleton domains or propagating any domain that gets reduced, and then finally preparing the search space by doing a domain reduction before starting search at all, which we saw greatly optimized or greatly reduced the number of steps and computations that we needed to do. I hope it was enlightening, and I'll see you on the next one.